So moles are great, and the chemical equation relates in terms of moles and moles because moles are related to numbers of particles, and that's how atoms and molecules react. The problem is we cannot measure compounds in moles. We measure them generally by weighing. And so we need to somehow introduce mass into this because we're interested in, if I have 5 grams of this, how many grams of that could I make? And so we need to put mass in here. And so here, this little guy here, right here, is the big picture of stoichiometry. The idea is that you have a mass of A, and from that mass you can find the number of moles. We learned how to do that. It involves the molar mass. Moles of A to moles of B is what we learned just this afternoon, using the ratios from the balanced chemical equation. And then we take moles of B and convert it to a mass using the molar mass. There's no shortcut for this. Okay, I've had students say, well, why couldn't we do this or this? No, there's really no shortcut. This really is the easiest, fastest way to do this. And so my condensed version of this, which I would encourage you to just kind of chant to yourself, grams to moles to grams. That's the path. The path for these types of calculations is always the same, so that's kind of nice, as opposed to some of those crazy unit calculations we did. Grams to moles to grams. Grams to moles to grams. You know, if you wake up with that running through your head, then you know that you're starting to get it. So let's look at an example. So here is the balanced chemical equation for burning octane. It produces carbon dioxide and water. What mass of carbon dioxide would be emitted by an automobile per 5.0 times 10 to the 2 grams of octane used? So from 5 times 10 to the 2, which is 500 grams of octane, how much carbon dioxide would be emitted? Okay, so this is going from a mass of one thing to mass of another thing. And so this comes down to grams to moles to grams. So let's first organize ourselves. What mass of carbon dioxide? So I find carbon dioxide in the equation and I put a question mark there. Mass is going to be in grams. So I write that under there. That's what I'm looking for. And then they give me 5.0 times 10 to the 2 grams of octane. Now you might say, well, I don't know what the formula for octane is. Yeah, but you know that O2, CO2, and H2O are not octane. So it's got to be the other one, right? So there's the mass of octane. So I've got a number and I have a question. So we're going to start with the grams of octane, and we're going to go to moles of octane. Grams to moles of CO2 to grams of CO2. Grams to moles to grams. Now look at this. Here we have grams of octane and moles of octane. The octane part isn't changing. The unit is changing. We're changing the unit from grams to moles, but still talking about the same substance. In the middle, the unit is staying the same, but the compound is changing. And at the end, the compound stays the same and the unit changes. You can only change one thing at a time. You can't change the compound and the unit. You can't go from grams of one thing to moles of something else. Good luck finding a conversion factor. You could create one, but in doing so, you'll have to do these steps anyway, so it's really a waste of time. So grams of the given thing to moles of the given thing to moles of the things you want to grams of the thing you want. And so this is our path, and this tells us what to do in our equation. So we're going to start with the mass that they gave us, 5.0 times 10 to the 2 grams of, you have to write the formulas in here, octane. We're going to have 3 conversion factors. And our path here, these are the units. We start out with grams of octane. The next one is moles of octane. And then we're going to have another term. After moles of octane comes moles of CO2. And after that comes grams of CO2. This guy right here is the key to the whole problem. I really, really encourage you to write that down. That's like your map, okay? You know, who do we call when we don't know which way to go? We call the map, right? And the map tells us, start with grams of octane, then go to moles of octane, and then go to moles of carbon dioxide, and then go to grams of carbon dioxide. And we say, oh, thank you, I forgot what I was doing. There it is, just literally written out for you. It's a beautiful thing. Because we get confused, we get lost, we start calculating, and then we're like, whoa, what was I doing? I don't even remember. You go back, there it is, right there. So those units go straight across the top. Then we need to cancel out some units because we got all these crazy units in here. So we take this one and we want to put that in the bottom of the next one so it'll cancel out. C8H18. Then we've got grams. Oh, I wrote it in the wrong place. So I'm zoomed in and I can't see. There we go. I want it down here. Because grams of octane divided by grams of octane is 1, and that basically disappears. In the next one, we want moles of octane, because these guys are going to cancel out. And then in the last one, we want moles of CO2 in the bottom. So we have this pattern, this kind of a diagonal pattern with our units canceling out. Any questions? This is really, really important. Now we have to put some numbers in here. The middle one is the easy one. That's the one we just learned how to do. That comes from the balanced chemical equation. 2 moles of octane are going to produce 16 moles of CO2. 16 is in front of CO2, so in my ratio here, I'm going to put 16 in front of the CO2. In the equation, 2 is in front of octane. That means 2 moles of octane, so I'm going to put a 2 down there. And yeah, you could simplify that to 8, but just let your calculator take care of it. This term and the last one involve molar mass, and we've already learned how to do that. So we're going to calculate the mass of 1 mole of C8H18. And I encourage you to actually write this out. 8 times 12.01 plus 18 times 1.008 equals 8 times 12.01 plus 18 times 1.008 equals 114.22. Now, if you're clear on what that is, you don't necessarily have to write units in your little notes to yourself down here, but I'm going to write them in, at least this first time. That means that 114, let's see, I'll just keep that 4 in there too. 114.224 grams of C8H18 is equal to 1 mole of C8H18. So this number goes with grams. So we'll put it right in here, 114.224. And then we also need the molar mass of carbon dioxide. So that's 12.01 plus 2 times 16, which is 44.01. 44.01 grams of CO2 is the mass of 1 mole of CO2. So again, the number goes in front of the unit gram. The molar mass is the mass of a mole. So don't put the number in front of mole and say that 1 gram is this many moles. It's always 1 mole. The units that you already put in tell you where to put the numbers, whether you're multiplying, dividing. Now just go across from left to right, multiply by anything on the top, divide by the bottom. Some people like to multiply and divide by ones, that's fine, but you can also skip those. It ends up being the same. And I encourage you to do it twice, because it's very easy with all these numbers to make a little mistake. So 5 times 10 to the 2 divided by 114.224 times 16 divided by 2 times 44.01 equals. And this is a big number. I'm going to bring it up top here. My calculator says 1,541.18224. And the units will be grams of CO2. That's way too many significant figures, isn't it? Mole ratios are exact. Molar masses are generally not going to limit our answer either. So look back and see, where did you start? This had 2. So that means that I need to round this off to 2 significant figures. But I can't just call it 15, because 15 is very different than 1,500, right? So we need to put this in scientific notation. So it's 1.5 times 10 to the 3 grams of CO2. And that is the mass of carbon dioxide emitted by an automobile burning 500 grams of octane. Any questions? We're going to do more examples. Same equation. What mass of octane would be needed to generate 42.3 grams of water? Well, let's write these numbers under the equation so we can identify what we're doing here. What mass of octane? That's a question. How many grams of octane? And generating 42.3 grams of water. So this kind of looks backwards of what we just did, where we had the octane and we were calculating one of the products. But the process of doing the problem is exactly the same. I've got a mass of something and I'm finding the mass of something else. So our path is going to be grams to moles to moles to grams. This time we're starting with grams of H2O to moles of H2O to moles of octane to grams of octane. Grams of what you're given to moles of what you're given to moles of what you want to grams of what you want. So 42.3 grams of H2O. 3 terms. Our map is telling us where to go. Grams of H2O to moles of H2O. Next in line, moles of C8H18. Yeah, it's a little tedious, but go ahead and write that formula out. And then, not enough room, oh well, C8H18. It's hard to get perspective when you're drawing on a little part of the screen. Someday I'll have to bite the bullet and buy a full-sized iPad. So we got the top fixed, grams to moles to moles to grams, and then we put the bottom units in, so they're going to cancel out. And moles of H2O and moles of C8H18. Get all the units in, cancel them out, not just how you wish they would cancel out, that's wishful unit cancellation, but how they actually cancel out. And then we need numbers. Well, the middle one's easy. I think it's often a good idea to start with easy. So here we go. C8H18. The mole to mole ratio comes from the equation. There's a 2 in front of octane, so I want to put a 2 in front of octane. There's an 18 in front of water, so I'm going to put an 18 in front of the water. This last one, we already calculated that molar mass, so we don't have to do that again. It doesn't really fit in there. We'll force it. Then we need the molar mass of water. 2 times 1.008 plus 16 gives us 18.016. So that's going to go in here, 18.016. Start at the left and go straight across. 42.3 divided by 18.016 times 2 divided by 18 times 114.224 equals. So that big old mess equals 29.8 grams of octane. I rounded that to 3 significant figures because my starting number had 3 significant figures. If my starting number had 9 or some crazy large number of significant figures, then my molar masses would limit, because these are limited to most likely 4 significant figures. Any questions? Okay, so let's do this example. Bless you. Everybody's got hay fever. One component of acid rain is sulfuric acid, which forms when sulfur dioxide, a pollutant, reacts with oxygen in rainwater according to the following reaction. So there we have our balanced chemical equation. Assuming that there's more than enough oxygen in water, how much sulfuric acid in kilograms forms from 2.6 times 10 to the third kilograms of SO2? So one thing they're doing to you in this problem is they're throwing kilograms in there. But notice that you're given a mass in kilograms and you end up with a mass in kilograms. So there's 2 ways that we can do this. Actually, there's more than 2 ways. Let's do it this way. Let's convert the kilograms into grams. So 2.6 times 10 to the third kilograms. That's going to be kilograms on the bottom, grams on the top. Kilo means 10 to the third. This should be a review. So that ends up being 2.6 times 10 to the 6 grams. And that will be less troublesome. So that's the mass of SO2. 2.6 times 10 to the 6 grams. The question is, how much sulfuric acid? Now it wants kilograms, but we could calculate grams. and then convert it. So we don't have a lot of room on this slide. I'm going to write our path up at the top. Grams to moles to moles to grams. Grams of SO2 to moles of SO2 to moles of sulfuric acid, H2SO4, to grams of sulfuric acid. That's our path. So then we're going to translate that into one big old equation. I'm going to start with the mass of SO2. 2.6 times 10 to the 6 grams of SO2 times, we want moles of SO2 there. Grams to moles of the other thing, H2SO4, and then finally 2 grams of H2SO4. You with me? Grams to moles to moles to grams. Those are the units that go on top. There's always going to be your initial number and then 3 fractions. We take the grams of SO2 and those go down there. So this unit is going down here because we want those to cancel each other out. So those cancel out. Then this unit, moles of SO2, goes in the denominator in the next fraction. Moles of SO2. And then those units cancel out. Moles H2SO4 goes in the denominator of the last one. There's a very firm pattern here, and it always ends up the same. The units are different, but the pattern is the same. So down here, we've got moles of H2SO4. And those cancel out. Everybody okay with units? Now we put numbers in. The one in the middle is easy. It's from the equation. We've got moles of H2SO4, and so we look in the equation and we see that in front of H2SO4 is the number 2. So we write 2 in front of H2SO4. What number is in front of SO2? 2. So I'm going to put a 2 there as well.
So that's always given, right?
Yes, that middle term of moles of one thing to moles of another always comes from the balanced chemical equation. Always, always, always. There's no calculating to do. You just look at the equation, find that compound or element, whatever number's in front of it, that's what goes in that conversion factor. Yes?
On the test, would you ever have a question where you have to write out the equation, balance it, and then do this?
No, no. That's more of a Chem 1 level question. You know, it's like, well, sulfuric acid and sodium hydroxide reacted and you had this many grams, how many grams of product would you make? And I gave you words and you have to turn them into formulas and then predict the products, balance the equation, and then do the stoichiometry. Okay, that's a whole bunch of skills all rolled into one, right? So I'm not going to do that to you. Yeah, you're welcome. I do want, you know, yeah, I'm not going to say anything. But there's plenty of skills rolled into this type of a calculation. Working with units, understanding what the chemical equation means, and being able to calculate molar masses. We have to be able to do all of those things together. But we're not going to throw balancing and predicting products in with this. The first term and the last term are always going to be a molar mass. So SO2, sulfur is 32.07, and 2 oxygens 32.07 plus 2 oxygens, 64.07. And this little bit of, where'd my arrow go? This little bit of scribbling down here, I really encourage you to do that. Because say you're doing this on Mastering Chemistry, and you do this whole big thing, and you put the answer in, and it says incorrect. You don't want to just start all over, right? That's what it sounds like when you see that, right? It's really snotty to you. You don't want to have to start all over. If you write things out like this, you can go back and check. Go back and look, okay, SO2, yeah, that's the mass of sulfur. I didn't, accidentally pick tin or some other S element. And here's 2 times 16, that's the mass of oxygen. Yeah, that one's okay. And you can go back and check each little step and make sure that you did them correctly. Whereas if you don't write anything down, you have to start over. So I'm not a fan of starting over. Maybe you are. So 64.07 goes in here. That's a 0. Then we need H2SO4. So 2 hydrogens, 1 sulfur, and 4 oxygens. Two times 1.008 plus 32.07 plus 4 times 16 equals 98.086. And that is the mass of 1 mole of sulfuric acid. Now we need to do the math. So we've got 2.6 times 10 to the 6 divided by 64.07 times 2 divided by 2 times 98.086 equals. And I'm getting this really, really big number. I have to move up here to write it down. And what's the unit on that? Grams of H2SO4. Bless you. What did the question ask us for? Kilograms. So we need to convert this to kilograms. Bless you again. So 1, 2, 3. I need to move the decimal point over 3 places. What I'm doing here is grams on the bottom, kilograms on the top. Kilo means 1,000. I'm dividing by 1,000. So that gets me a little bit more reasonable of a number, 3980.3902 kilograms. How many significant figures should that number have? 2. So that means I'm keeping the 9. Okay, we need space. Make some space here. So 3980.3902 kilograms. We want to keep the 9. The 3 and the 9. We look at the next number, it's an 8. That means we round the 9 up to a 10, which rounds the 3 up to a 4. So this is 4.0 times 10 to the what? Well, third. 1, 2, 3 kilograms of sulfuric acid. Sorry for the mess. 10 to, yes. Try again. Thank you. Times 10 to the 3rd kilograms. There we go. But you see how putting a box around the answer really just like makes it jump out at you? so you can find it, because I went all over the place. Questions? I know that some of you are still working on Chapter 7, but I would encourage you to start working on these problems as soon as possible. The sooner you start working on them, the fresher lecture will be in your mind and the easier it will be. If you wait until next Tuesday to work on them, it's not going to be good. So there's my piece of advice.